Hey Chem 30s, it's Manchak here with a recording for you of a video lesson for concepts D4 and D5. So just as a recap, what you should have covered to this point in the unit is you should have gone through concept D1, which explained equilibrium and what equilibrium is all about, and really zoomed into looking at how equilibrium occurs for us in a system, a chemical system, as opposed to maybe a solubility or some other kind of system. We spent some time looking at last week writing and interpreting how we represent systems at equilibrium. We defined what the equilibrium constant was and talked a little bit about extent of reaction, whether a reaction is complete or whether it favors the reactants or products. We talked about equilibrium law expressions. And we spent some time working with some numbers that allowed us to either calculate a Kc value or to use the Kc value to help us calculate concentrations at equilibrium, for example. You'll seem to recall maybe an ice table involved in there. And something, or an ice cube, or whatever kind of pun you wanted to. I saw another teacher talking, playing Vanilla Ice in the background, because it's just a plain old ice table, so it's kind of vanilla ice anyway. We also then talked about Le Chatelier's principle in concept D3, and Le Chatelier's principle was all about what happens if an equilibrium or system is at equilibrium, and we mess with something in that system. And the three things that we messed with were concentration, temperature, and then pressure/volume. Okay, so that's where we're at right now. This unit, if you recall, is called chemical equilibrium, focusing on acid-base systems. So where we are getting to now into D4 is we're transitioning now into acid-base systems, and we're going to start to talk about them again. And if you recall, when we took Chem 20, I told you when we did Chem 20 that when we got into the latter parts of Unit C, I said, I'm telling you the truth right now, as it stands until you get to Chem 30. So here we are in Chem 30, and what I'm going to do is I'm going to actually change up, or we're gonna broaden our definition of what chemical equilibrium is all about, and we're going to broaden our definition of what acids and bases are, because there were still a few blanks to be filled in for us, and I'll get to those as we get into the lesson. I am going to do this video in two parts for you, so or this week in two parts. So this video I will introduce D4 and D5 to you, and then I will record just the D4 information. Then I'll hit stop, upload that video, and then you guys can see the D5 stuff on Bronsted-Lowry acids and bases later on. So in concept D4, what we're going to do is we're going to have a quick look at water, and water is going to be the bridge the bridge that sort of spans the gap between where we were last year and where we're going to this year in trying to understand what's going on with these. So we're going to talk about the water ionization constant and how that relates to pH, pOH, hydronium and hydroxide ion concentrations, as and play around with those ideas. Then when we get to D5, what's going to happen is we're going to jump into Bronsted-Lowry. And Bronsted-Lowry is sort of our new theory of what acids and bases are all about and how they work. And it broadens our appreciation for what acids and bases are, and allows us to explain more situations where something may not appear to be an acid or a base when we look at its chemical formula, but for some reason it's reacting as an acid or base. Okay, so that's where we're headed to in this concept. And D5 is relatively straightforward. As a plus, if you think about this is our second last week of lessons, because all we have left then are to cover D6 and D7. D7 is very, very quick. D6 is a little bit more involved with some more complicated calculations in it, but nothing that I know you guys can't handle. So I think with that, that is all I'm going to say about D4 and D5 and in that intro. And what I'm going to do now then is talk to you guys about what we're going to be covering in concept D4. So in D4, we're looking at water ionization and its constant and what that is. So it's going to give us a deeper picture of acids and bases. And then we're going to revisit pH, pOH, and then we're going to link acids and bases to equilibrium and talk about something called percent ionization right at the end. I've selected 3 videos that I think are pretty good. They a lot of them sort of really glaze over D4, and so don't stress that too much. They kind of glaze over them a little bit. I will hopefully do a good enough job explaining that you guys won't have any issues with it. And then there's so some of these videos are kind of looping back and forth between D4 and D5, but I definitely have a look at them. And for D4, it is this line master I want you guys to look at, LSM 16.1C, which is KWP PHPOH calculations. Have a look at that one and do that one once you've done this video lesson. All right, so I am going to drag that off screen so I have access to it later, and we are going to move on to our PowerPoint. So if you guys have your notes in front of you, you can follow along with me on this. I'm just going to resize myself a little bit. So we are going to start to talk about water a little bit here, and I'm going to sort of set the stage for you in the first couple of slides, and then we'll get going from there. So we've already learned several concepts about strengths and properties of acids and bases. And if you wanted to go have a look at page 262 of your textbook, you certainly can do that because there is lots of good information in there. What we're going to do is try to fill out our definition as you guys reach the end of high school now of what acids and bases are. As you move on to chemistry and post-secondary, there will be more out there. I'm not saying that this is the way things are always and forever, but for now, this is going to round everything out for us. So what we're going to do now is we're going to try to combine equilibrium theory and acid-base concepts together to get a more complete understanding of how acids and bases work and what they're all about and why they do the things that they do. So for simplicity, we have been using the hydrogen ion. If you remember concepts in our concepts in Unit B, whenever we had an acidic solution, we've just put H+, to represent an aqueous hydrogen ion. This works well, but I want you guys to remember, back to what we learned in Chem 20, that hydrogen ion is so incredibly reactive that it will almost instantly in an aqueous solution find a water molecule, grab onto it, and become H3O+. Okay, so do remember that as we move forward here. So I'm just gonna remind you using my little pen up here, right? If we had an H+, which is basically just an exposed proton, and it comes near a water molecule, okay, remember water looks something like that when we do our correct 3D structure. Remember that this end over here is slightly negative and this end here is slightly positive. This being positive, this being negative, there's going to be an attraction between the two. That's going to create our hydronium or H3O1+ molecule. So do try to remember that as we move forward. So let's then talk about the water ionization constant. And this might mess with you guys a little bit. So if it does, that's okay. We learned last year in the acid-base unit in Chem 20 that even very pure water has the ability to conduct a little bit of electricity, right? So when we did some of our comparisons in some of our labs, we did talk about the fact that even though we're detecting conductivity and we're trying to figure out conductivity of something, we always try to communicate it as conductive as pure water or more conductive than pure water, because pure water does conduct a little electricity. Okay, and this has to do with the fact that water particles actually ionize, only very seldom, into something in pure water. So in pure water, there is actually an equilibrium established, and that equilibrium that is established is between, let's say, 2 water molecules and then hydronium and hydroxide ions. And what's happening is very, very rarely 2 water molecules will collide with the right orientation and the right amount of energy in order to, and this is our orientation that we're looking at down here, in order to create so this is the orientation here, in order to create a hydronium ion and a hydroxide ion. Okay, and if we draw up this equilibrium equation, you can see that the equilibrium equation very strongly favors the reactants. So it is a less than 10 to the -6% of water molecules are going to collide to create the hydronium and the hydroxide. So water is really not very conductive, but there is a small amount of it that is conductive. And that small amount that is conductive is enough to is enough to cause a particular reaction that will create and establish an equilibrium that will create hydronium ions and hydroxide ions. So let's work with that. Let's keep this in the back of our minds. Okay, so this equilibrium very strongly favors the reactants, which is water. And if we look at the Kc for the reaction, we find that we can eliminate the bottom two here. Why do we eliminate those? Well, remembering back to where we've come from, anything that it is in a condensed form, like a liquid or a solid, is ignored in our equilibrium law expression. So really, our equilibrium constant for that reaction is the concentration of hydronium times the concentration of hydroxide. Okay, I'm going to keep building on this, so follow along with me. Evidence has also suggested that fewer than 2 of every billion water molecules are ionized, thus suggesting that the Kc is very small. Well, we're going to put a number to it. In fact, the water ionization equilibrium relation is so important that it has been given its own symbol and name. We call it the ionization constant for water, or Kw. Okay, so K subscript W. And we represent this as 1 times 10 to the minus 14 moles per liter. And luckily for you guys, that is something that is referenced in your data booklet. If you look on page 3, okay, right in here, water ionization constant, or the dissociation constant, there it is right there, up on the screen there for you, at SATP. Okay, so based on what we can say above, then we can then assume that the concentration of hydronium or the concentration of hydroxide is in this when we establish this equilibrium is 1 times 10 to the minus 7 moles per liter. Okay, we just created over here a perfect square. Again, we took the square root of that side, which meant we took the square root of this to get this value. I hope that kind of makes sense. I'm not going to get too deep into the mathiness of it. And one of the videos that I linked does a pretty decent job explaining how we arrive at it. So what do we do with this? Why do we care? Okay, well, let's rewind for a little bit. Okay, water. We say pure water has a pH of 7. Right, pure water has a pH of 7. And we're going to get to this in a second. So this might blow your minds, or it might just make you really confused. I don't know. Hopefully we can work our way through it. So if water has pure water has a pH of 7, okay, and we just said that in pure water, when it establishes that equilibrium with an equilibrium constant of 1 times 10 to the minus 14, that the concentration of hydronium and the concentration of hydroxide in that pure water is 1 times 10 to the minus 7. Now, I don't know if you guys recall how to work between pH and pOH, but we're gonna jump into that again now. Okay, so hold that thought in your head. Okay, so just to go back, when we established the equilibrium that we talked about up here, okay, we are talking about an equilibrium with a constant of 1 times 10 to the minus 14, very strongly favoring the reactants. And when we simplify this and try to solve for a concentration of hydronium or hydroxide, we end up with a concentration of 1 times 10 to the minus 7 moles per liter, okay, for each of hydronium and hydroxide in pure water. All right, so where do we go with this? Well, where we're going with this is one of the best things about Kw is that it applies to pure water, meaning that this constant can be applied to any solution that is mostly water. Being that acids and bases are dissolved in water, we can take a leap that this applies to them, with the caveat that they are not highly concentrated. Okay, so since the mathematical relationship above is so simple, we can use Kw to calculate either the hydronium or the hydroxide amount concentration if the other concentration is known. But the certainty of Kw is then lowered to 2 significant digits due to the presence of other substances besides pure water. Okay, so just a couple of caveats in there for you guys to consider. So this is where we're getting that from. If we know that our equilibrium law expression is this guy up here, okay, then if we wanted to solve for hydronium ion concentration, it would be Kw over hydroxide, right? All I did was divide by divide by hydroxide and divide by hydroxide on both sides in order to rearrange it correctly. Hydroxide ion concentration is then Kw over hydronium. Okay, fairly simple, fairly straightforward kind of stuff. So what we're going to do now is we're going to go through a couple of examples, and I'm going to hit pause in a moment here, and I'm going to show you how to work with this a little bit, and then we'll jump back into a few more notes when we get into pH and pOH stuff very shortly. So I'm going to hit pause. It's going to seem like I wasn't gone at all, but I'm actually going to take a couple seconds. Whatever. Here we go. All right, so I'm back. Got all that set up, and here we go. So in this question, remember we're dealing here right now with this equivalence, that the Kw, or the equilibrium law, or the equilibrium constant for this expression, which is hydronium ions times hydroxide, the concentration of those two, that's what we're dealing with. Remembering that this is 1.0 times 10 to the minus 14, and recall that we don't have a value, a unit, that's the word I'm looking for, a unit for the Kw value. So a 0.15 mole per liter solution of hydrochloric acid at 25 degrees Celsius. Remember, the temperature is not going to factor in, but we're including temperature because if we mess with temperature, we mess with the equilibrium constant. So if I'm using 1 times 10 to the minus 14, we're going to assume that we are at 25 degrees Celsius, because otherwise things change a little bit in there. So we found that solution of hydrochloric acid at 25 has a hydronium ion concentration of 0.15 moles per liter. Remember, hydrochloric acid is a strong acid, and one of the things that we said, and we will say coming up again in the future, is that whatever the concentration of your strong acid is, that's also the concentration of your hydronium ions in a strong acid only. Okay, we're going to get into a little more detail on that in the next concept. So we need to calculate the amount concentration. Remember, amount concentration is moles per liter, right? That's what we're calculating, amount concentration. Some of the videos are going to call it molar. That means moles per liter of the hydroxide ions. Okay, so this is super simple. We know that we have this, that our equilibrium constant for this equation is equal to, this is our equilibrium law expression, and we're solving for concentration of OH. So the concentration of OH is Kw over the concentration of hydronium ions. So it's going to be 1 times 10 to the minus 14 over 0.15 moles per liter. Okay, and then you'll just grab your calculators out and calculate away. So it'll be 1 times 10 to the minus 14, okay, divided by 0.15. Okay, because we're using the a very large exponent in here, please make sure that you're using the little e, or that you're using brackets around the 1 times 10 to the minus 14. Otherwise, you're going to mess up operations in there. So this becomes 6.7 times 10 to the minus 14 moles per liter. And I want to just take a second here to think about this, and this is a bit of a review going back to Chem 20 with us. If we say that we have a 0.15 mole per liter solution of hydrochloric acid, that means that solution is acidic, okay? But it also means that because there's water in there, and it's a dissolved solution and all that kind of stuff, there are hydroxide ions present, okay? But in very tiny amounts, okay? Because if your pH is high, your pOH is low. If your hydronium ion concentration is high, like we have here with this solution, hydrochloric acid, then our hydroxide ion solution or concentration is very low, and they move opposite to each other, right? So something very acidic has a high hydronium ion concentration and a low hydroxide ion concentration. But what happens is, as that acidity decreases, the basicity increases. Then when they're equal, please remember that is this expression up here. When we establish that equilibrium between the water molecules colliding to make hydronium and hydroxide ions. That means that we have equal concentrations of hydronium and hydroxide, 1 times 10 to the minus 7 moles per liter, which is what we talked about in the last slide, which is the equivalent of a pH of 7, right? Because each of them has an equal concentration, okay? Once we go past this, and I forget which hand I was using to do stuff. I think it was this and this. So acid or hydronium hydroxide. So once we go past this, then our hydroxide ion concentration is high and our hydronium ion concentration is low. So if it's a strong base, they're very, very far apart. The weaker the base, the closer they get together. Once they are equal, we have something that is considered to be neutral, and then we go in the opposite direction, very strong acid. So that means that very low hydroxide ion concentration. And as that acid gets weaker and weaker and weaker, that they come closer and closer together. I hope that made sense to you. Okay. So what I'm going to do is just quickly tab over here and have a look and see what we got coming up next. So we got another calculation. We're going to do that one together, and then we'll move on. So I'm going to just switch back to this screen, and we'll toss this out of the way, put her down on the floor there, and grab at it. So here's the next one. Calculate the amount concentration of hydronium ions in a solution of barium hydroxide. Okay, so this one we can do relatively easily, but it's sorry about that. Had a little bit of a coughing fit there, but I'm good, and I got my water handy over here. Where is it? There it is, just in case I have another coughing fit. So this one is a little bit tricky. So a couple of things. First off, it's asking us to figure out the concentration of hydronium ions. Okay, well, we're dealing right now with barium hydroxide, which you guys should recognize as a base. Okay, so we're going to have a little bit of fiddling to do to figure this out. First thing I want to point out to you guys, and something that I know caught many of you in Bio or in Chem 20, is that barium hydroxide. We know that it is a we know that barium hydroxide is an ionic compound. It's an ionic hydroxide, making it basic. But we know that it dissociates when we put it in water. So it's going to dissociate into barium ions, and it's going to dissociate into 2 hydroxide ions. So why I'm pointing that out, and why I think it's so important to point it out, is that whatever the concentration of this is, the concentration of the hydroxide ions is 2 times the amount, because there are 2 hydroxides for every 1 barium hydroxide. So when we put that into solution, that when it dissociates, we have 2 times the hydroxide ions that we do hydronium or barium hydroxides. So what I want you guys to get from this then is that the concentration of hydroxide ions is going to be 2 times the concentration of the barium hydroxide. Okay, because there are 2 moles of hydroxide for every 1 mole of barium. Okay, so that means then our concentration of hydroxide ions is 0.50 moles per liter. Now, with that said, what is our hydronium ion concentration? Because we've got our hydroxide ion concentration. What is our hydronium ion concentration? Well, we're going to use our water ionization constant again to sort that out. Okay, and we're going to go 1.0 times 10 to the minus 14 over our hydroxide ion concentration, which is 0.50 moles per liter. Okay, and then that again just gets plugged right back into your calculator. So it'll be 1.0 times 10. Oops, messed that up, didn't I? 1.0 times 10 to the minus 14. You don't have to put the 0.0. It can just be 1 times 10 to the minus 14. And we're going to divide it by 0.5. And we're going to get 2.0, don't forget your significant digits, times 10 to the minus 14 moles per liter. So what this is telling us now is this is our hydronium ion concentration. Okay. That means that and that's a very tiny number, 2 times 10 to the minus 14. So that's telling us at this point that our concentration of hydronium is very small. That tells us then that we are dealing with something very basic. Well, we are, because we're dealing with an ionic hydroxide here. Okay, so that is that. Now, what I wanted to do with you guys is I'm going to leave that last example. I believe if I click to the right spots here, yeah, there's one more example. I would like you guys to try to tackle this example on your own. So if you want to hit pause right now, go ahead and do so. And then you can go and check your textbook on page 715 for the answer. I'm trying to shorten my videos down a little bit, so that's why I'm doing this. Okay, so hit pause now and do that example, and then I will be back in a moment with the next thing. Okay, so I hope that example went well for you. If it didn't, track me down. We'll figure it out. Fire me an email or something like that. So I'm going to make myself a little bit smaller here. There we go. So communicating concentrations, pH, pOH. I want to just go back and circle back to this for you guys just so we're all on the same page. Remember in Chem 20, we sorted out that to figure out the pH of something, we need to take the negative log of the hydronium ion concentration, whatever it is. And remember your log button, right, is the button right here on your calculator, that one underneath my finger there, right next to the 7 key. Just going to look for the one that says log. If you have a different calculator, I could help you find it too. And that the hydronium ion concentration, if we wanted to figure that out, is 10 to the negative pH, whatever it is, 10 to the power of the negative pH. Remember, we're dealing with a log scale here. And some of you may be doing logs right now in math, so this might make a little bit more sense to you than it did in Chem 20. And then for pOH, it's exactly the same formulas. All we've done is swapped hydronium and hydroxide. Hydronium and hydroxide. Okay, that's what we've done. Based on the above and the value that we have for Kw, we can also conclude that if we added pH and pOH together, it should equal 14.00 at SATP. I won't go into the math behind that, but if you wanted to go and figure it out, you could, and it's relatively easy if you just think of working with sort of these equations here and playing around with it a little bit and seeing what you're sorting out, right? Turning your hydronium ion concentration into a pH, turning your hydroxide ion concentration into a pOH, adding them together, you're going to get 14 no matter what you do. It's kind of fun. So next thing then. Just to recall that, we're going back to that. So for Chem 20, we define, we're getting into the acids and bases and talking about strength, and now we're bringing in the equilibrium stuff to this, okay? So recall from Chem 20 that we define strong acids as ionizing quantitatively, okay? We also use the word completely when we talked about that. Quantitatively, by reacting with water to produce hydronium ions. This is going to be true this year. Don't worry about that. And we said that weak acids, on the other hand, only ionize partially, usually less than 50% to produce hydronium ions. From the perspective of this unit, and where you guys have been doing your thinking now, this should look a little bit like equilibrium, right? This should look like a quantitative reaction, a complete reaction. And this should look like something that establishes an equilibrium that favors the reactants, okay? So based on what we know about equilibria, we can say strong acids, when added to water, react virtually completely or quantitatively to form hydronium ions and an anion, right? That should sound like using, there it is, our single arrow in this unit, okay? That should make pretty much sense. Notice I have a hydrochloric acid here, which is a strong acid. Oh yeah, that reminds me. How do you figure out whether something is a strong acid or a weak acid? Just to remind you, we've got this table in your data booklet on pages 8 and 9, okay? And right up here, these guys up here are your strong acids. So anything above the hydronium ion is considered to be a strong acid. So that is your perchloric and hydroiodic, hydrobromic, hydrochloric, sulfuric, nitric, those acids up at the top there, right? All of those are considered to be strong acids, meaning that when added to water, they react virtually completely to produce hydronium ions. Weak acids, for example, something like acetic acid, CH3COOH, reacts only partially to form hydronium ions. So a less than 50% reaction. You'll notice in here, when we've written this out, there's our double arrow again, okay? And there is our percentage above that, and this is 1.3%, which is much less than 50%, right? Right. So we've written out our reaction. Okay. Hope that makes sense to you guys. So the hydronium ion concentration of any acid solution can be calculated by multiplying the percent reaction by the initial amount concentration of the acid solute. I'm going to show you an example in a second here. For any aqueous strong acid, we assume that the hydronium ion concentration is equal to the initial concentration of the acid dissolved. That's that 100% reaction, or 99.9% reaction. For weak acids, okay, so remember this is strong acids. For weak acids, which is what we mostly encounter, we'll always need to calculate the hydronium ion concentration in the solution. There are 6 acids, we've already talked about those, that are considered to be strong acids. And if you forget them, you've always got your data booklet. I don't know what I'm doing. You've always got your data booklet handy if you need to. Okay. So here's the little formula that we're going to use for this next calculation. And this is our percent ionization calculation. So this is sort of your root formula up here at the top. Okay. I'm going to change to my little laser pointer thingy so you can see it better. So this is your root thing at the top here. And then down here, we've got it rearranged to solve for the hydronium ion concentration. Remember, P here means percent ionization. So how complete is the reaction? Is it 99.9%? Is it 1.3%? It's basically communicating to us how much of the strong or weak acid has been converted into hydronium ions. Is it 99.9%? have been converted to hydronium ions, or is it 1.3%, or whatever number we're playing with, okay? HA, and we're going to use this from time to time, HA is the generic reference for initial concentration of a weak acid. Remember, we're going to talk about weak acids with this because in a weak acid, we have less than 50% or less than 100%. In a strong acid, we're just going to say whatever that concentration is, that is the concentration of our hydronium ions. All right, so let's jump ahead. Next example. So I'm gonna set things up again, and then we're gonna jump into this. So I'll be right back. All right, and we're back. So, but I wasn't even gone for you. It's so weird how this stuff works. Anyway, so here's an example of how we might work with something like this. In a 0.1 mole per liter solution of acetic acid, only 1.3% of the acetic acid molecules have reacted, or if you guys recognize from last unit, ethanoic acid, have reacted at equilibrium to form hydronium ions. Calculate the hydronium ion amount concentration. So hydronium ion amount concentration, okay, remember amount concentration is moles per liter. So we're going to calculate that. How are we going to do that? Well, we're going to use that formula that we had on the last slide, which is the concentration of hydronium ions. What was it again? How do you remember? Let's just bounce back to that so you guys can see it again. Okay, so we're going to go back here, and we want the concentration of hydronium ions, so we're going to use this formula here, which is our percent ionization divided by 100 to turn it back to a decimal, and then multiply it by our weak acid concentration, whatever that is. So it is going to be B over 100 times the concentration of our weak acid. So it's going to be 1.3%, right? Because there is our percent ionization divided by 100 times the concentration of our weak acid. There's the concentration of our weak acid. How do we know it's a weak acid? Well, it's not one of the 6, right? We said that it's acetic acid. Acetic acid is not one of the 6 strong acids. So we're going to do that times 0.10 moles per liter, okay? And that's going to give us a fairly simple answer to sort out, I would hope. I'm sort of getting in my way here. Okay, so we're going to do 1.3 divided by 100, which probably most of you guys can do in your head, and that's fine, times 0.1. So that gives us 0.0013 moles per liter, and I'm looking, I've got 2 significant digits up here, 2 significant digits in the 1.3%, so that should be my final answer there. So what is the concentration of hydronium ions in this? Well, it is 0.0013 moles per liter. I'm going to take this just one step further with you guys because I want to sort of preview where we're going for the next couple of slides. If we know the concentration of hydronium ions, then we can figure out the pH, right? Because pH is the negative log of the hydronium ion concentration. Remember why I told you we use pH? We use pH because it's a little easier for us to communicate how acidic or basic something is. Because otherwise, what ends up happening is people get confused. Yeah, well, you know, it's got a hydronium ion concentration of 0.0013 moles per liter. Well, what does that mean to the person who hasn't studied Chem 30 before, right? So that or has forgotten everything they studied in Chem 30, which is also a possibility, which happens to many of us as time goes by. So then all we're going to do to get the pH is we're going to take the negative log. And then I'm going to hit second function and answer because I've already got that answer plugged in on my screen. And it's going to give me a pH of 2.89. And why I chose two decimal places there is because our significant digits are 2. So the number of decimal places in your pH has to be 2. If it was 3 significant digits, then you'll have 3 decimals in your pH. Does that make sense? Okay, so that's example number 4 done and done. And I believe our next example is coming up in the next lesson. So I'm going to just quickly tab out of here, back to here, and we're going to jump ahead to the next couple of slides. So I'm gonna leave you guys again to work your way through example number 5 on your own, please, and you can find. And see what you come up with for the answer. If it doesn't make any sense to you, then track me down and we can fiddle with that together. Okay. So where I'm going to jump to now, that's basically this video for concept D4. Where we're going to go next then is we're going to jump into D5 in the next video. For you guys right now, please remember that I asked, I'm going to bring this back over here, that I asked for you to do this LSM right here because it's going to just be a little bit of work with KW and what's going on there, and then some practice using pH and POH again, which we're going to have to do when we get into concept D6. Okay, so that's it for this video. Please remember to ask me questions if you have any questions about anything, and then I am going to go ahead and record, and you guys can watch D5 video, which is the one that follows this, but I would do the worksheet in between while this stuff is still fresh in your minds. So that's it for now. We will talk very soon in D5.